Chapter 4, Sample Problem to Elongation Due to Weight. What you see here on at the l- top left, it's a oil creek which sends a steel pipe uh, well below the ground in depths of 12,000 feet, passing three layers of soils using three different shafts with the same material of A36 steel, but different cross-sectional area, different unit of weight, and also different length. Uh, we are interested to see what is the normal stresses inside each of these pipes, uh, as well as the free end of the elongation of tree end of the at the far beyond the below the ground at the depths of 12,000 feet. To approach this problem, if we start from the free end D and we just take an element of E by the length of X from CD, and because the weight of CD is 2 pounds per feet each feet, so if we do have X feet of length in our element, that's the force of 2x applied as a tensile force at each both ends of CD. Likewise, with the same logic for 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 part CD, for shaft CD, we do have a 2 point x pound per feet. So if we consider an element of x, it's 2.8x plus a hanging weight of shaft CD, which is 2 times 2000 feet, which is 4000 pounds force, which applies as a tensile force to both ends of BC. Likewise for AB, for let's say AB, for shaft AB, the unit weight is 3.2 pound per feet. So if you take an element of X, it's 3.2x plus a hanging load of both 4,000 feet plus 2.8 times 5,000, which is 14,000, 14 plus 4, which is 18 extra dragging force of a tensile force at both ends of BC. So then if we want to see what stress is, what the stress is inside each of these pipes, sigma BC, sigma B, sigma A, sigma B, sigma C. So start with the uh, last one or easiest one, which is force over area, 4,000 tensile force over cross-sectional area of 1.225 inches. For the second part is a 2.8 times 5,000, which is 14 plus a hanging force of 4,000 addition added to the previous one over a 1 and 3/4 of square inches in cross-sectional area. It goes to the very first one, which is 3.2, the weight per unit feet times the length, plus a combination of 4,000 plus 14,000, 4,000 plus 14,000 of hanging weight. And if you do the math, it gives you 13.6 KSI, 10 point for AB, 10.3 KSI for sigma B, and 3.2 KSI for sigma C. And KSI stands for kilopound square inches, which is the unit of stress, normal stress in US customer unit. And then for delta D, elongation at the far end D, let's uh, do it. Hmm? So the interesting part about this part is that we do have three separated different blocks. So that's a summation, and each of them has a unit weight, so that's incremental, a continuous loading. So that's combined both those categories, which uh, we talk about that in chapter video chapter 4 part B in details. And if any of you, and it just goes by an integration from 0 to 2000 for shaft CD, the force of 2x dx, and integration of that over the cross-sectional area over the modulus of elasticity of A36 steel, which is 2910 to 6 PSI in US customer unit. Then for the second part from B to C, it's 0 to 5000, 2.8x plus the addition weight. And for the first one is 0 again to 5000 of depths of 3.x, which we calculated in previous slide, and a hanging load of 4000 for the middle one, and 80,000 for the very first one, which the two others are attached from the very first one. And by doing this integration, we will reach to a delta D of a 2.99 feet, which is an interesting problem which combines both summation and uh, integration at the same time. Mhm. Another solution for that, which is far easier, and it's based on the approach which I just provided in chapter 4 axial load part B video, and I will put the video in description if you haven't watched that video, and that's make the problem far easier avoiding those integration with this method. So if but from data we know the weight of each part. BC is 2 times 2000, 2 pound per feet times 2000 feet, which gives me 4000 pounds force. WBC is 2.8 times 5000. The weight of the only part BC is 14,000 pound, and weight of BA alone is 3.2 pound per feet times 5,000 feet, which gives me 16,000 pounds force. And delta D is a delta D with respect to C plus delta C with respect to B plus delta B with respect to A. Again, if we want to solve the problem without integration, a delta D is just a combination of the three of addition of three sections. And for example, delta DC start from the very last one, from the free end, which is the easier part, and it just says instead of to avoid integration, uh, instead of integrating the load, just put half of the weight at the free end. So the total weight is 4000. Half of that is 4000 over 2 pounds. So we just convert a distributed load of W to a concentrated load of W over 2 at the end of that section. So that's nothing but 4000 over 2 pounds times NL over EA. And if you do so, it gives a numeric value of 0.1103 feet. Likewise for the second part, BC, delta BC is a 2.8 times 5000, which gives you 4000. Convert the distributed load of W, which is 14,000, uh, uh, and apply that as a concentrated load of half of that at the end C. That's 14,000 over 2. And but don't forget that in second part we do have extra weight which is hanging from the end C, and that's not going to be half. That's a 4,000, a separated box of 4,000 hanging from our second part. So that's additional weight to a W over 2. That's 4,000 plus W over 2 in terms of pound time. That's our N times L over EA. That gives you 1.084 feet. Likewise, do the same for the first part. BE is the weight of uh, 3.2 pound per feet times 5,000, which gives you a 16,000. Convert that distributed load to a concentrated load of half of that amount, which is 16 over 2. But do not forget the two addition, 4,000 and 14,000, which are the two other shafts hanging from the very first one. They are not going to be halved again. So that's our normal force times 5,000 feet over EA again, and it gives you 1.7931 feet. And if you add them up together, you will reach to a numeric value of 2.9874, which almost is 2.99 feet, like the solution 1 uh, uh, answer. And that's the interesting part, is just with uh, these three lines you avoid that integration process. Thank you.